Hey everybody, and welcome to ARI Live. I'm Chris Hopstock, our Architect Education Specialist here at Black Spectacles. I'm excited to be your host for today's ARI Live, which is all about structures. We're going to revisit a number of questions about structural design that you might see in either the PA, PPD, or PDD divisions. We're going to be joined by architect and structural expert Adam Kors, who's going to give us a fresh look at how to approach these questions and share some of his strategies. If you're joining us for the first time, Black Spectacles is the first ever NCARB approved online test prep provider for all 6 of the ARI 5.0 divisions. Our test prep includes video lectures, practice exams, flashcards, and virtual workshops, all available online, with memberships available for either individual architects, firms, AA chapters, or schools. If you're curious about how you can get your whole firm on a membership and have your boss pay for it, go to blackspectacles.com and head to our pricing section. I'll share a link in the chat for that now. We're also the first test prep provider to offer an ARI guarantee. If you use our expert membership to the fullest and don't pass the ARI, we'll pay for your retake. I'll share a link in the chat with more info on that as well. We also have some exciting developments around our ARI study materials. We just rolled out something that everybody's been asking for, quizzes for both PPD and PDD. And actually our guest Adam today wrote a number of those questions. So thanks Adam for that. In total, we released about 200 questions to help you improve your performance on exam day by reinforcing your recall with our quizzes. In addition to PPD and PDD section quizzes, we've launched brand new study materials for CE and upgraded our virtual workshop exercises for all 6 of the ARI divisions. We'll be adding new study content all year round, so stay tuned to see what's next. Now, we know the licensure process can be overwhelming, and at our next ARI Live broadcast on April 14th, from study strategies and testing order to understanding licensure requirements by state, we'll share the key things that you need to know to get started with the ARI and become a licensed architect. Today, we will be engaging exclusively in our ARI community online, so head over to that thread if you haven't already. You can either click the link that I just shared in the chat box or find it under the ARI Live section of our ARI community homepage. Everyone who posts on our thread today will be eligible to win a free Black Spectacles t-shirt. So head over to community.blackspectacles.com and just say hi. Don't forget to stay tuned until the end of the podcast to see if you've won. I'll share the link in the chat box and you can find it in the episode description if you're listening after the live broadcast. So without further ado, I'd like to welcome our guest, Adam Kors. Adam is a licensed architect in Illinois at Graham and Hyde Architects, and he specializes in advanced technology, industrial, and the educational markets with experience in both architectural and in a structural capacity. So welcome, Adam.
Thanks for having me.
Oh, nice to have you. So like we mentioned before, we're going to be doing a little bit of a different format today. We'll start by playing a clip of a previous ARI Live session, and then we'll break it down and discuss it with Adam. So let's get started with our first question.
Okay, for our new high school gymnasium in Denver, Colorado, the architectural and development team has reviewed and analyzed the geotechnical report during their initial preliminary design process. So we're talking very early on, preliminary process. The ownership team, the development team has gained the geotechnical information. They've gone to geotechnical, so soils engineers essentially. They've presumably done some testing out on the site, and they have a written report that has been given to the development team. The report shows that the first 12 inches of the soil is organic material. So whenever you see organic, when you're talking about soils, what that tells you is you cannot build on top of it because the organic will change size and shape as it decays over time. Whenever you see the word organic in relationship to soils, know that that's not something you're going to use, so you can cross that one off. And then from 1 foot to 6 foot, the soil is a silty mix with a potential capacity of approximately 1,200 PSF, pounds per square foot. And then from 6 foot to 8 foot, the soil is a salty sandy mix. These terms sound sort of funny, the salty sandy mix. They actually often get even longer. They, silty, salty, sandy, like it's a whole kind of crazy long list, but it's just sort of talking about the mix of sand, silt, gravel, clays, boulders. So just depending on the mix, you'll see a different set of descriptors. So, okay, the soil is a silty, sandy mix with a potential capacity of approximately 1,500 PSF. So that's from 6 to 8 feet down. From 8 feet to 55 feet, the soil is a gravelly sand mix with a capacity of approximately 5,000 pounds per square foot. And below 55 feet is a rock base with a potential capacity up to 8,000 PSF. Everything else is sort of straightforward in terms of blows per square foot and liquid limits. The water table is shown at 13 feet below grade. So everybody knows the water table is that point down below grade where the soil is saturated. You've all seen this when you've been at the beach and you dig a hole in the beach and it suddenly fills with water to a certain height. That's, you found the water table. If you go out to a job site, they start digging down and it fills with water when it hasn't rained. That means you've found the water table. Now, it's also possible you could dig a hole and it rains and it fills with water, and that's a different question. But if you're getting that water that's coming up from the ground itself and it's filling up to a certain height in the excavation, you've found the water table. So the water table being at 13 feet below grade, that's a useful thing because every time I dig below that excavation is going to fill with water.
So when we look at these types of questions, my recommended approach is to go through and instead of staring at all 4 choices as 4 choices, but rather go through and identify the ones that we can eliminate quickly. Obviously, with the exam, time is of the essence. So the first one that really jumps out to me is option D. That says there's no reason to review the soils information until there is a viable design or a viable approved design option, likely during the design development phase. This is actually probably one of the not great ideas you could do in this case, really because your soils report, while it does specifically give you the different soil types in a specific location, it really will help drive your design, not only from the structural system, but also in terms of where maybe you place the building on the site, what the building will look like based on the different soil bearing capacities. For example, you could have one section of the site that has really bad pressures, but if you move, say, 10, 15 feet over to any one direction, the soil properties change substantially, which then allows you to do maybe a more smaller footing versus the larger ones. So while you may not have it when you first start the project, sometimes you don't have it for a few weeks until after you're able to get access on the site, things like that. You do want to use it as quickly as you can upon receipt to minimize any backtracking in terms of the design work. So with that said, option D is one of the first ones we could remove as a possibility for this. The next one that I think can be removed would be option C. At first glance, option C seems like it would make the most sense. However, if you look at the prompt, or the scenario rather, it says, what is the likely location for the bottom of the foundation footing? Typically, when you put in your footing, you would like that the top of the footing to be at the frost level, frost depth or below. The reason being is by doing so, that entire footing is below frost, which allows for more stable temperature differences as the years go by, making for a more stable footing. By putting the bottom of the footing at the frost depth, it's effectively not going to do anything for you. Another thing to consider is if we look at our prompt, we see that we have a bearing capacity of 1,200 PSF from 1 foot to 6 foot. Typically, structural engineers like to see around 2,000 as a minimum, just for, at least in my experience, 2,000 seems to where they would like to be. So given those 2 answers, I think we can easily remove option C from that case. So that leaves A and B. Caissons to 56 feet to get the best rock soil capacity, and B at 10 foot below grade for solid capacity, but less expensive than caissons. Since we're at a gym, we're going to have a lot of clear open spaces just by the nature of being in a gymnasium. That's going to minimize the number of columns that we're going to have in our building. Typically, they're going to be just around the perimeter. So if we look at it from a cost per column, there's only about a 3,000 PSF difference between the 8 to 55 feet and below 55 feet. So we're not really gaining a whole lot in this case. Also, we need to look at where our water table is here. Since it's 13 feet below grade, anything below that, we're going to have to really consider how our foundation system is going to work in terms of do we need to add any additives to that mix to make sure that we have proper compressive strength in whether or not it's concrete or if it's just rammed aggregates. So if we look at this, option B is going to be the best answer in this case. We're at 10 feet, which means we're 3 feet above the water table. We've got good bearing capacity, with it being 5,000 square PSF rather. So for a gym, this is going to work ideally.
Thanks, Adam. That was great. And one more thing that I'll say about option D, if you look at these 4 choices, option D is really different than the first 3. The first 3 choices are really talking about 3 different options for where you could put the foundation elements, and option D is just saying sort of there's no reason to consider it at this time. And usually when you see an answer like that, it's not the right answer. So, all right, moving on to question 2.
Okay, we're going to take a look at number 2 here. While detailing the retaining wall for the garden entrance sequence, you realize you need to add the required reinforcing. Which of the following is the most likely? So the concept of a question like this is really just to see if you kind of basically understand the gist of like when we're talking about concrete, we're usually also talking about steel. We're doing reinforcing steel inside the concrete. And that concrete is spectacular at compression, but it is awful at tension. And so every place in that concrete element, whether it's a beam, a column, or in this case, a retaining wall, every place where we expect there to be tension, we're going to want to make sure that's where the steel goes. And every place where we expect compression, we don't really need to worry about putting too much steel there because the concrete can handle it just fine. And so the big question on something like this is, well, where is the tension and where is the compression?
So like Mike mentioned, concrete performs really well under compression, which is why it's the preferred material for foundations, where you're obviously going to have large compression loads, which are gravity loads from the building. And it does not do nearly as well in tension, and this is where the reinforcing rods are going to come into play. So when we look at a question like this, the first thing we want to do is identify where are our loads. So we want to sketch out just really quick where those loads are being applied to our retaining wall here. So in this case, we're going to have our soil that's pushing on the retaining wall. But not only are we going to have that force, but we're also going to have a moment in the footing as well, because as that soil is pushing on that wall, it's going to want to bend. Good example is this: is if you put your curve your hand a little bit and you start pushing on your fingers, the heel of your hand wants to start to bend the farther you push. So we're going to have a moment in this case where on the right hand side it should be in compression, and the left hand side is going to be in tension, because as that footing or that retaining wall rather moves, it's going to pull on that left-handed side and push on that right-handed side. So with the reinforcing rod, you always want to put that on the side that the wall is in tension. So as we look at this, the first one that could immediately be removed is option A, because if we look at our reinforcing in our retaining wall, the vertical portion, we can see that it's on that right-hand side, which is going to be in compression as the load is applied to the wall. The next one we can look at to remove is, let's look at option C, or D rather, I'm sorry. We'd see that, yes, we have our reinforcing on the tension side. However, it only goes up a portion of the wall, which means that that top half of the wall is going to be unreinforced, which is just the same as if there's nothing, it's just going to be one of the easiest spots for it to fail. So we can remove option D from this case. Now that leaves option B and option C. So if we look at option C, we see that the reinforcing bars are centered vertically and at the top of the foundation and the footing. This really isn't the best location for the reinforcing, because if you think about it, like we mentioned before, on your footing, the portion on the right, that reinforcing bar is actually going to be in compression in that case, not tension. Also, with the reinforcing in the center of the wall, it's really not going to do anything in this case because it is centered in the wall. For this, the best answer is going to be option B. You notice, though, it does have an additional set of reinforcing on the top right portion of the footing. A lot of times you may see this in your details. This is more so from a constructability issue. It's just easier to install that reinforcing across the entire top portion versus picking and choosing where it's actually needed the most. So obviously here, if we look at it, we have all of our reinforcing in tension. We just have that additional reinforcement there on the compression side just for my ease of construction. So B in this case is going to be the most likely reinforcement.
Thanks for going through that, Adam. And it's really easy to get tripped up on which side of a wall or which side of any structural member really is in compression versus tension. So, you know, I find that the easiest way to remember to figure that out is to just sketch it out like I've done here on option A. And you can see here, you just draw the neutral axis down this member. Everything on the right side of this member is getting squeezed together. It's shorter than everything on the left side of the axis. So that tells you right there that the right side is in compression and the left side is getting stretched. Therefore, it's in tension. And another thing I wanted to talk about, Adam, is I noticed these first two questions that you're going through. You're really using this process of elimination strategy, and I just wanted to ask you about that. Like, why do you find that to be a useful strategy, and how do you use it?
Well, I like to use it because when you look at an exam question, there's usually one or two that can rather easily be eliminated, and then there's one or two that are very similar, to where if we quickly eliminate those one or two options that aren't necessarily correct, it allows for more time to really look into and dissect those other options versus just looking at all four as a whole. So for me, that just seems to be a little bit of a time management deal, to where you're really only focusing on one or two, maybe three, versus all four.
Yeah, I think it's a great strategy. I mean, mathematically, it just improves your chance of getting the answer correct if you either don't know it or you know a little bit of the information required to answer it, but you're not 100% sure. You know, with this question, if you can just eliminate one answer, you've got that much better of a chance to get it correct. You go from 25% chance to 33% chance. So it's a great strategy. Moving along to question 3 here.
To finalize the schematic design for a single-story small gymnasium for the junior high school your firm is designing, you make a reasonably accurate best guess for the structural system for the 68-foot clear span. Choose one. We have Virendale truss, wide flanges, concrete slab, open web steel joists. So Virendale truss is it's just so likely to show up on the exam. It's a kind of old school architectural thing, and it's a weird one because it's a very specific truss that actually isn't a truss. If you think of what a typical truss looks like, where it's got all the diagonals, it's probably not a great version one, but let's add one more there. That's a kind of classic truss. A Virendale truss looks like this. Which is to say it's not a truss at all. Without the diagonals, it doesn't actually function as a truss. But architects, especially those architects from the 60s and 70s, love the Virendale truss. And it has this very cool, memorable name. And so it shows up all the time on the exam. And often you'll see these used as bridges, where the scale is so big that you can kind of walk through it. And architecturally, architects always love them because they don't, without the diagonals, the steel doesn't get in the way of the windows. So it can fit right into a sort of a typical architectural scene. But it's a very well recognized name, but not appropriate. It's very expensive. All of these have to be moment connections in order for this to work. It's a much more expensive system than you would use on something like this, unless there was some really big defining reason why you really needed to, and it doesn't say. So we're definitely not going to be doing Virendale truss, but you should know that term because it is likely to show up at some point. Steel wide flanges, so that's just kind of classic steel beams. Steel wide flanges could totally do 68-foot clear span, but it's not their sweet spot. Like a 40-foot span, a 45-foot span, even up to a 50-foot span is pretty reasonable. 40, 45 is typical. 50, you're starting to get pretty long. 55, 60, 65, you're getting pretty long there. You're going to have a very expensive system. So you could use wide flanges, but it's probably not the most logical for that particular span, given our other choices. So I'm going to say no to that one. Again, that's a correct answer, but it's just not as correct as one of the other ones. So then the last two are 6-inch flat concrete slab. It'd be hard to span 68 feet in a 6-inch slab. It could if we had it as a curve, like the ones that Candela and Nervi and people like that used to do. But a kind of classic flat concrete slab, 6 inches, 68 feet, you'd have to have an awful lot of rebar in there. And even with that, I don't think that would really work. So the answer we're going to talk about here is open web steel joists. And this is totally the sweet spot for open web steel joists, especially for the long spanning ones. They make a lot of sense for a single story. That means there's no floor up above. Why would that be important? Because the open web steel joists tend to be a little bouncy. And so you have to kind of over design them if you're going to have people walking on the floors up above. But if it's just the roof up above, and you don't mind a little bit of bounce and give, something that if people were walking on it might feel a little weird, but if nobody's walking on it, then who cares? Then the open web steel joists are sort of like a totally logical, straightforward potential at this clear span, and would be sort of the economic, logical choice for something like a small gymnasium. You can pretty easily do that kind of 40-foot to 70, 80 feet range with the open web steel joist. You can go shorter as well. The big advantage of the open web steel joists, right? These are the ones that look kind of like that.
The other big advantage, other than being relatively light and kind of comparatively inexpensive for the amount of steel you've got, is that they're open, right? So I can put duct work through them. I can, they don't weigh a lot, so they're not adding to a lot of heavy load to the building for foundation purposes and everything else. So there's a bunch of advantages to them. The big disadvantages, like I said, is that they do have a little bit of bounce. So in order to get the stiffness, they have to be pretty deep, but you're not using a lot of steel. And so that kind of back and forth, for this kind of length, they're really a logical choice for something, a project like this.
All right, Adam. So we've got another question here that focuses on a gymnasium. These are pretty classic question types, mostly because it's the typical or the classic type of building that you'll see where you're dealing with long span structures, which is one of the, it's definitely a structural system that's tested on the ARE. So what do you think about this question, Adam?
Absolutely. So again, if we want to look at our process that we've been going through, which ones can we easily remove? The first one that really jumps out to me is option C, the 6-inch flat concrete slab. So reason that I think this is one of those that can easily be removed is we're doing a gymnasium with a 68-foot clear span, and we've only got a 6-inch rather concrete slab that's going to span that full 68 feet. That is a very long span for a 6-inch concrete slab to span. By the time you put your, you've got your own self weight of the slab, plus the hanging weight from your sprinklers, your ductwork, your lights, any gym equipment, as well as loads such as snow, your RTUs, things of that nature. Deflection is really going to start to be a concern in this case. So when you really think about it from a gym standpoint, this is not the best case for, or the best use rather, for a concrete slab construction. So we can easily pretty well remove option C. The next one, it may not seem like the case at first glance, but option A, the Vierendeel trusses. The reason why these would not be the best option in this case, because a Vierendeel truss utilizes just vertical members. They do not have any diagonal reinforcements, which from an architectural standpoint is a very aesthetically appealing truss. However, they are very heavy and very expensive because all of those vertical connections to be structurally sound have to be moment connections. Moment connections are very labor intensive, very expensive. A typical truss, that's why you have that diagonal bracing in there, is to help get that load dispersed rather easily. So given this case, again, this is probably not one of those cases or instances where you would use for this application. So we can remove option A. That leaves B, steel wide flanges, and D, open web steel joists. So both of which could be used in this case. Typically with steel wide flanges, which are your I-beams or your W flanges, you want to stay about 40 to 50 feet is their preferred range, where they're the most economical. When you start getting into these larger spans, the beams tend to get rather large. Another thing you want to take into consideration here is that W flange is going to be one solid piece of steel. So when you start thinking about running your ductwork, any sprinkler lines, things of that nature, your building is now going to have to get taller because you'll have to go under that beam. You can't utilize any of that, that joist space for structural steel, or for your mechanical systems rather. Whereas an open web steel truss, or steel joist rather, as it says in its name, is an open web, meaning that ducts, sprinklers, other equipment can pass through those relatively easy, shortening the span of your building. In addition, they come in many different profiles. They can span up 68 feet, kind of like the sweet zone for an open web steel joist. You can get them in curves for a barrel roof. Think of it like the joist profile would be like a archer pulling back on his bow. They call it a bowstring. You can get more shapes with a less additional steel. So in this case, option D, the open web steel joist, is going to be the best case for this application.
All right, and moving on to question 4 here.
For a small 2,000 square foot single story field house project deep in a beautiful park area that is under consideration, the client, the park district, gives the architect the geotech report, which clearly states that the soil capacity in the predetermined site area below the organic material that makes up the first 18 inches, so the very top material is organic, and so we're not going to use that at all. But below that is a comparatively poor silty sand of approximately 1,000 PSF, pounds per square foot, down to about 20 feet deep. It does note, however, that there is a very high quality bedrock soil at approximately 65 feet deep with a capacity of 8,000 PSF. The one-story building should probably be considered in which of the following ways? A, 60-inch diameter caissons at column points to the bedrock. B, raft or mat construction. C, bearing wall with strip foundations. D, steep angle roofs to shed snow to reduce the snow loads.
So if we look at this, upon first glance of the question, option D can be eliminated rather quickly. While a gable roof will shed snow relatively easy, it's not going to be a high consideration in this case. Snow loads typically are going to be a higher consideration in the design of the roof framing members, as those are going to take the direct blunt of that snow load, and your foundations are only going to take a portion of it as it's distributed through the different columns of the wall system. So for that reason, we can eliminate option D from the consideration. Next one, in my opinion, that is relatively easy to eliminate is going to be option A, the 60-inch diameter caissons at the column points to the bedrock. The project's only about 2,000 square feet, so it's really not all that large. And the 60-inch caissons are going to be way more capacity than what's actually going to be required to support the building. While the 8,000 bearing or 8,000 PSF 65 feet down is a desirable bearing capacity, it's really not necessary for a building of this scale to be able to justify the costs associated with those caissons. So in this case, we're going to want to eliminate the option A. So that's going to leave B, a raft or mat construction, or C, bearing walls with strip footings. C, with a building that's only 2,000 square feet, typically C would be the preferred installation method for a foundation on a building of this scale. However, if you look, we have to go 20 feet deep to get to decent bearing capacity on our soil test. That is a long ways for a narrow bearing wall strip footing foundation. So in this case, the preferred option would be a raft or mat construction, because now we can use that entire 2,000 square foot footprint and only have to dig enough for maybe a 2 or 3 foot deep concrete mass that the building is going to sit on instead. So if you think about it, a raft foundation is just effectively a large block of concrete that the building sits on, versus a bearing wall, which just has a narrow strip foundation around. So you now get the full use of that 2,000 square feet on your 1,000 PSF bearing capacity. So when you look at it from a load standpoint, that application is going to be more than appropriate for this instance.
Thanks for that explanation, Adam. And this is another question similar to one that we saw earlier, where one of the options just really stands out as being different than the others, and it's really smart that Adam eliminated that one right off the bat, option D here. Kind of similar to the other one that we talked about. These first three options talk about different foundation options that you can choose, and then the last one talks about solving the issue a totally different way by altering the roof in some way. And if you think about it from the perspective of somebody trying to write these questions, they have to come up with not only the right answer to the question, but three other plausible options that they think somebody might choose. So if you were writing a question and the roof answer here was really the correct answer, you probably wouldn't make three incorrect answers that are totally different from it. It wouldn't seem like somebody would choose those. So just a little bit of psychology and trying to get into the mind of the question writer when you're trying to answer these questions. All right, well, thanks again, Adam, and thank you all for joining us. Be sure to register for our next ARI Live broadcast on April 14th, where we'll share the most important steps for getting started with the ARI so that you can all become licensed architects. I'll post the link to register in the chat box in your GoToWebinar control panel, or you can go to go.blackspectacles.com/ARI-live to sign up. As I mentioned at the top of this webinar, we've launched our ARI Guarantee. We're confident that if you use your expert membership to the fullest, you will pass the ARI. If you don't pass, we'll simply pay for your retake. To learn more about how to qualify for the guarantee or to check out our individual memberships and see what kinds of materials we offer, go to blackspectacles.com, and under the ARI prep heading, you'll see a section on our guarantee. And I am sharing a link in the chat for that as well. Also, to learn more about how you can get your whole firm on a membership and have your boss pay for it, go to blackspectacles.com and head to our pricing section. Just shared a link to that in the chat box as well. We'll be announcing our t-shirt winner in the Black Spectacles community today, and we'll reach out via email to get your size and shipping information, and congrats to the winner. Just a reminder that if you'd like to be eligible to win a t-shirt, post a question you have about our feature topic in our ARI community during the next ARI Live, or simply say hi. Just drop any sort of comment in there during the live. And our community is always buzzing. It's not just active during ARI Live, so feel free to poke around throughout the month and see what your fellow architects are up to and asking about. Finally, be sure to stick around for a few minutes today to take our survey and share any suggestions that you might have. I promise we read every word that you write and use them to fine-tune our upcoming episodes. Thanks for watching.